Welcome to today's Explainer. We are taking an absolute plunge into deep space. We're going to examine a galaxy that literally looks like a sliver of light in the dark, and we're using some of the most detailed astronomical data out there to dissect it, piece by piece. We're unraveling the mysteries of Caldwell 26.
To really appreciate what we're dealing with, let's anchor ourselves to the sheer scale of the cosmos for a second. Our target sits exactly 14.25 million light-years away. That means every single photon of light hitting our telescopes right now, it started its journey over 14 million years ago. Just let that sink in.
So what is our exact destination? It's Caldwell 26, or as it's beautifully nicknamed, the Silver Needle Galaxy. You'll find it hanging out in the Canes-Venatici constellation. Now, it's a spiral galaxy, kind of like our own Milky Way, but it presents this very specific, entirely unique viewing angle to us here on Earth that makes it an absolute goldmine for astronomers.
Which brings us to a really fascinating question. What kind of secrets hide within a galaxy viewed perfectly on edge? Because when we look at the Silver Needle, we're not looking down at some swirling vortex. We are looking at it completely flat, right from the side.
Think of this edge-on perspective as an astronomical cheat code. Seriously, if you look at a face-on galaxy, sure, you get a gorgeous view of the spiral arms, but the bright core completely washes out any faint, delicate structural halos around it. But an edge-on view, it totally blocks that blinding core and reveals the vertical structure. We get to clearly see the thin disk, the thick disk, and any subtle weird warping taking place out at the edges.
And because all that intense bright light is concentrated along that thin silver line, deep optical observations can reach incredibly faint surface brightness limits. We're talking around 27.5 magnitudes per arcsecond squared. To translate that into plain English, it is phenomenally dark. It lets us see the absolute faintest ghosts of stellar structures hovering around the galaxy, which actually sets up our very first mystery.
With optics that insanely sensitive, astronomers fully expected to see a massive, extended gaseous halo surrounding the galaxy. I mean, it's a really common feature in spiral galaxies. Usually, intense star formation pushes a ton of gas out of the disk. But when they looked at Caldwell 26, nothing. It just wasn't there. So the big question became, where in space is the galactic halo? To solve this, researchers turned to the Halo Gas Survey. They pointed the Westerbork Synthesis Radio Telescope right at the Silver Needle for a staggering 120 hours. That is basically a 5-day, non-stop cosmic staring contest. And the results were definitive. There was strong evidence against a significantly extended halo. Now, at first glance, the galaxy's disk appeared to thicken at the edges, which you might mistake for a halo. But the radio data proved this was just an optical illusion. It's actually a line of sight warp in the disk itself. On top of that, they found the galaxy has a super low star formation rate, only 0.12 solar masses per year. It simply doesn't have the violent stellar engines needed to blow a massive gas halo out into space.
So the big takeaway here is that Caldwell 26 is incredibly calm. And this is further backed up by a concept called kinematic lag. Basically, this is a negative gradient in rotational velocity as you move higher above the galactic disk. Put simply, gas higher up rotates slower than gas in the midplane. In the Silver Needle, they measured a lag of -9 kilometers per second per kiloparsec. That precise, undisturbed lag, it's exactly what you'd expect to find in a quiet, slow-forming environment that hasn't been dramatically shaken up by exploding stars or major galactic collisions. But wait, if the Silver Needle is so calm and undisturbed, we run headfirst into our second astronomical detective story. When zooming in from that missing outer halo, right down to the main body of the galactic disk, astronomers noticed a completely startling anomaly at the extreme edges. Why do the stars just stop? To understand this, scientists map the individual stars at the edge using a color magnitude diagram. This is a brilliant tool that allows astronomers to categorize stars by age, separating out the young blue main sequence stars from the old red giant branch stars. And what they found was honestly mind-bending. The stellar disk doesn't just gradually fade out into the darkness of space. Nope. Both young and old stars alike suddenly hit an invisible wall at the exact same radius. Boom, they just stop. Just how sharp is this wall? Well, the stellar density abruptly drops by a factor of 600. 600! And that happens over a mere 5 kiloparsecs, which is a relatively tiny slice of astronomical real estate.
A drop-off that drastic means something is fundamentally interfering with the outer edges of this galaxy. If the galaxy is too calm internally to create such a sheer cliff face, the force has to be coming from the outside.
All right, let's look at the leading dynamical theory here. Step 1. A standard extended galactic disk forms over billions of years. Step 2. Invisible dark matter subhalos. These are dense, invisible clumps of mass left over from the formation of the universe, constantly bombard the galaxy, whizzing straight through the disk. Step 3, as these dark matter clumps blast through the outskirts where the galaxy's gravitational grip is the absolute weakest, they act like giant cosmic scissors. They violently strip the stars away, leaving behind that sheer, sharply truncated edge we observe today. Wild, right?
Moving into Section 2, the nuclear heart. Zooming into the rotating core of Caldwell 26.
To get the complete picture of Caldwell 26, we have to zoom all the way in from those stripped macroscopic edges down to the microscopic center. Exactly at the center sits a nuclear star cluster. Studies by the Royal Astronomical Society, which actually used adaptive optics to peer straight through the galactic dust, revealed that this central cluster isn't just a random grouping of stars. It's a highly flattened, remarkably dense structure that completely dominates the core.
Let's unpack the data captured by the Gemini telescope, because the numbers are staggering. This tiny cluster packs a mass of 1.6 million solar masses, and it is spinning incredibly fast, with a clear rotation of 30 kilometers per second confined within just the central 10 parsecs. The stars in here are absolutely buzzing with energy, featuring a central velocity dispersion of 28 kilometers per second. Plus, just like the broader galaxy, it features a distinct mix of a young blue disk component and an older red spheroidal component. What we're looking at is a bizarrely massive, rapidly spinning heart that is kinematically distinct from the sluggish gas disk of the wider galaxy.
This poses a massive question for astrophysicists. How exactly did this heavy, spinning heart form? Well, there are two leading theories in a fierce ongoing debate right now. The first is gas accretion. This is the idea that raw gas from the main galactic disk falls directly into the center, spins up, and forms brand new stars right there on the spot. The second theory is cluster accretion, where preformed star clusters from farther out in the galaxy lose momentum through dynamical friction, and they slowly sink into the center, eventually merging together to form this supercluster. To test these theories out, scientists built advanced particle dynamical models. Think of these as incredibly complex computer simulations that map out how millions of stars interact gravitationally over massive amounts of time. And these models provided a major clue. They proved that the nuclear star cluster in the Silver Needle couldn't have assembled more than half of its mass just by eating other sinking star clusters. Because it's spinning so uniformly and contains distinct young flattened populations, direct gas accretion from the disk absolutely must play a massive role. Which honestly brings our explainer perfectly full circle today. As this quote from the research highlights, the assembly history of nuclear star clusters can, in principle, be inferred from studies of their stellar populations and kinematics. By mapping out the tiny, microscopic details of this rapidly spinning cluster at the very center, we are actually unlocking the billions of years of history of the entire galaxy, from the gas falling into the core to the dark matter violently stripping its edges. And that leaves us with a pretty profound thought to walk away with. Caldwell 26, our beautiful silver needle, gives us a perfect edge-on mirror into galactic mechanics. If this calm, distant galaxy has its edges violently sheared off by invisible dark matter subhalos, and its massive heart is fueled by infalling gas, what unseen forces are quietly sculpting the edges of our very own Milky Way right now? Thank you for exploring the cosmos with me today. Keep looking up and keep asking questions.